afternoon and welcome to the SETI Institute Lunchtime Colloquium Series. Generally for this series we have visiting scientists come present their research projects to us, but this Tuesday we are having our scientists in training present their summer internship projects. These are our 14 REU summer interns. My name is Jean Shar and I'm the current director of the REU program here at the SETI Institute. This is the 9th year that we've run this very successful internship program. The students have been asked for today to prepare a 3-minute, 3-slide synopsis of their summer research program. We're going to hold them pretty strictly to their 3 minutes. They will get a warning bell when their time is running out. And if you hear the bell, students, it's time for you to finish up your sentence and make room for the next student. If you are the next student in line, please be ready to come up when it is your turn. We will hold all questions for the students and for myself until the last speaker has gone. Okay, and with that, I will start my 3-minute, 3-slide introduction to the SETI Institute REU program. Hello, again, my name is Jean Shar, and I'm an astrophysicist here at the SETI Institute. I recently took over the reins of the REU program from Cynthia Phillips, who has led this program for the last 8 years. This program is funded by the National Science Foundation. This summer, we have 14 students who are working with SETI Institute scientists for a 10-week internship program. They are doing their research at the SETI Institute and at NASA Ames. All of their research projects fall under the category of astrobiology. They include topics such as physics, astrophysics, computer science, planetary geology, and astronomy, to name a few. The students have carried out their projects here and at NASA Ames. They've done field work, they've carried out computer simulations and modeling, and have worked in the lab, just to name a few things. Our SETI Institute program is nationwide in that we select students from across the country. This year, students are from Cal Poly Pomona, CSU, Fresno, Long Beach, and Los Angeles, San Jose State, just down the road, Bowling Green State University, Columbia University, Embry-Riddle, Ohio State, University of Illinois, University of Maryland, and University of Rochester. The students from the California colleges are recruited under the Compare program, which is run by Alex Rudolph at Cal Poly Pomona. The students will tell you about their individual research projects, but I will tell you about some of the other experiences they've had for this summer. For one, they've attended the weekly colloquium from visiting scientists, and of course they are taking over today's colloquium session. But following the previous colloquia, they have had a chance to talk with our visiting scientists and have a casual pizza lunch with them after that. They made a trip to Lassen National Park to do some studies of extremophiles. They also spent some time at the Allen Telescope Array and were able to make observations there. And they got a lucky nighttime personalized tour of the local Lick Observatory. So I'd like to thank Edna DeVore, the director of our EPO program here at the SETI Institute. I'd also like to thank Alex Rudolph and Matt Povich at Cal Poly Pomona. And I'd like to thank the mentors, of course, for mentoring these great students, and the support staff here at the SETI Institute for making this program extremely successful. And finally, I'd like to thank the National Science Foundation for providing funding for this research. Okay, and now with that, I'll turn the floor over to our first student, Abigail.
Hello, my name is Abigail Holmes, and I'm a senior in astronomy at the University of Illinois at Urbana-Champaign. And today I'll be talking about my research with my mentor, Dr. Zhonghee Rou, to analyze the near-infrared spectra of several galactic supernova remnants. By near-infrared, I mean light with wavelengths of about 1 to 2.5 microns. And this light is dispersed according to wavelength so that you can see the relative intensity at different wavelengths. And that allows you to characterize the molecules and atoms that are present in an object. And that's what a spectrum is. And then supernova remnants are these structures of ejecta and disturbed interstellar medium that are created by a supernova. So most of my summer was spent doing data reduction, and I did that primarily using the SPECS tool, which was created by Dr. Michael Cushing. The first step in this is to subtract a background frame from your object frame, and you do that to remove any features that are due to anything surrounding or in front of the object you're interested in. And then you also use a dark frame to account for noise in the detector, and a flat frame, which allows you to account for pixel-to-pixel differences in readout. I would do a wavelength calibration so that I could say a specific feature was present at a certain number of microns, as opposed to just saying, well, it's in the middle of the spectrum. Then I would combine my data sets, because I normally had multiple observations, sometimes from several nights. And I would do a telluric correction, which allowed me to account for the Earth's atmosphere, and a flux calibration so that I would know the intensity of the different, the different lines. My data came from the Palomar triple spectrograph, which was on the Palomar 200-inch telescope. This is an example of one of the raw data frames. Most of the lines you're seeing are not due to the object you're interested in, but are actually due to emission from the Earth's atmosphere. These are my results for the supernova remnant W49b. Most of the lines that you're seeing labeled here are due to the REU vibronic transitions of molecular hydrogen. There is one iron line present in the H band. The reason why this is interesting is because the ratio of the different hydrogen lines can be used to tell you about the shocks that are going through the remnant, because you know about the excitation of the hydrogen. And these are my results for CAS A. There are only 2 lines marked here, and they're both iron lines, and part of the problem here is that the data are very noisy. And so compared to the previous spectra, which you can see look very clean, these ones, they have a lot of ups and downs that aren't really relevant. And part of the problem here is that there wasn't a good way to account for the atmospheric emission, because it was too variable here. So I'm going to be spending the rest of my time here trying to find a way to better reduce this. And that is all. Thank you.
Hi, my name is Lindsay Schroeder. I'm an engineering physics student enrolled in the accelerated dual degree program at Embry-Riddle Aeronautical University. My project for this summer is titled An Investigation of the Streamline Geometry of Photoevaporative Winds from Planet-Forming Disks, on which I worked with my mentor, Dr. Umar Gorti. I'm going to begin by giving a little bit of background on circumstellar disks. They are large masses of dense gas and dust that exist in the wake of the formation of young stars, and they are the birthplace of planetary systems around these stars. They exist for very short timescales, of a few million years, after which the photoevaporative wind from the central star blows the gas out of the disk, leaving only the solid planets and planetesimals to remain. My project specifically dealt with adapting my mentor's existing disk model to include the streamline geometry of this photoevaporative wind, and then examining the changes in the density and temperature distribution throughout the disk based on the different streamline geometry models. In addition to a no-wind control case, we utilized 3 different models, the first being a relatively non-physical but kind of a simple overview cylindrical wind in which the gas flows directly upwards from the disk. The second model was a constant angle model in which a theta is specified at which the streamlines are directed away from the disk. And then the final model is a converging angle model at which the streamlines diverge from a point below the disk and then outward through the disk. The applications of this is important because it affects the different streamline geometry, affects the mass loss rate throughout the disk of the photoevaporation, and which in turn affects the likelihood and composition and distribution of planets forming in these circumstellar disks. And I will be presenting this work at the AGU fall meeting in December. Thank you.
Hello, I am John Derby. I'm a physics major at Cal Poly Pomona, and my mentor was Dr. Jean Shar. My research was modeling carbon dust around evolved carbon stars. These stars are old red giants that are losing mass in the form of gas and dust and produce most of the dust in the interstellar medium. This dust comes in aromatic and aliphatic dust types. The aromatic is the cyclic hexagons. The aliphatic is the more chain-like molecule below it. This is the first systematic study with a range of known hydrogen atom fractions from aromatic rich, that's fewer hydrogens to total atoms, to aliphatic rich, that have more hydrogens to atoms in the molecule. I picked one well-studied extreme mass-losing carbon star, IRS 07134 plus 1005. It is a 21 micrometer object that is low metallicity and carbon rich. My first couple weeks were spent finding initial conditions. These include photometry from 0.4 to 100 micrometers from the 2 micron all-sky survey, IRAS, the SIMBAD database, and Mixner from 1997. The spectra are from Quark's ground-based observation in 1990, and the Infrared Space Observatory as published by Cox in 2009. Some of the parameters that were more constrained for my model were the dust geometry from observations, the stellar temperature from the spectral classification, and the angular size, also from observations. Parameters I varied more were aromatic to aliphatic grain type, opacity, and the dust grain size. The result of all this modeling was a lot of spectral energy distributions which covered a wide range of fluxes and wavelengths. This is my best match SED. I call it that because it matches the stellar emission and dust emission continuums relatively well. It does not include any emission features as we would expect at 3, 7, 11, and 21 micrometers. The carrier for the 21 micrometer feature is as yet unidentified, but we would expect the 3, 7, and 11 features to come from aliphatic compounds. The problem with these is that it's hard to get their feature to continuum ratio and the overall emission feature to match at the same time. I therefore conclude that a better model would be an average of more aromatic compounds like the one seen here and more aliphatic compounds that would contain the emission features. One thing that can change be fixed in the near future is making the dust emission continuum plot below the 21 micrometer feature. And that's it. So.
Hi everybody, my name is Marina Gemma, and this summer, under the guidance of my mentor, Dr. Jason Rowe, I've been working on a project that statistically validates Kepler planet candidates using Speckle imaging. I focused on one particular Kepler object of interest, KOI 297. KOI 297 had a clean light curve with a high signal-to-noise ratio and was a previously unvalidated system. This system has one planet candidate, and if the transit signal that Kepler detected does actually represent a planet, it would most likely be a potentially rocky, heavily irradiated planet, much like Kepler 20e that you can see in an artist's conception on this slide. So to validate a planet, you need to eliminate the potential that the transit signal we see is a false positive. There are numerous astrophysical phenomena that can cause a transit signal, like the ones Kepler detects. One particular scenario is the presence of a background blend, where a star in the background of the KOI field of view alters the flux of a light curve, mimicking a transit signal. So my project attempted to eliminate the possibility of a background blend for KOI 297. Here we have a graph that plots separation in arcseconds versus delta magnitude. The colored regions are parameter space in which a false positive source can be excluded. And the Kepler data is fantastic in that it eliminates a good chunk of parameter space on the graph. So the Kepler aperture tells us that any star beyond 2 arcseconds can be eliminated, and the transit depth of the light curve tells you that any star fainter than 6.3 magnitudes cannot cause a transit with the depth that we see. And if we were to use Kepler data alone, we could validate planetary candidates to the 90% level, which is a fantastic statistic. But if we want to be really sure, we can use Speckle imaging to further eliminate parameter space on this graph and lower the possibility that we are looking at a background blend. So we can compare the Speckle data to a galactic model for the KOI field of view to estimate the number of potential stars that are not detected by Speckle imaging. And we can apply this estimate to the entire Kepler field of view, and when we do that, we can expect about 17 background blends for the entire Kepler field of view, which is 160,000 stars, so that's a pretty good number. So through analysis like this, we can say it's statistically unlikely for a transit signal that we see to be a false positive and validate planetary candidates in this way. So being able to validate one planetary system at a time is a first step to a larger process. So we don't want to just validate one system at a time like on the left, but we want to move towards a method of bulk validation on the right. So I have Speckle data for 600 KOIs, and the next steps in my project involves automating this analysis process to exclude or include these as planetary candidates. Thank you.
Hello, I'm David Vega, and I'm presenting you my work in the image quality for dim stars and asteroids observation using GPI. First, let me quickly introduce you to the GPI. It is a project that has about 70 scientists, and the instrument itself is installed in the Gemini South telescope in Chile. This new instrument is in its commissioning phase. That means that we just started to obtain data and calibrating and testing the instrument. Its first flight was just back in November 2013. The instrument counts with 3 observing modes, which all use adaptive optics to correct for the turbulence introduced to the light while it passes through the Earth atmosphere. Those 3 modes are direct imaging, coronagraphy, and polarimetry. Right here you can see all the 3 modes. The one on your top right-hand side is the coronagraph mode, where we block the light from the star and we can observe directly planets. The one on the bottom right, it's the one that we can that we do polarimetry, and we can observe some other light filters from the objects. And the big one is the asteroid palace being directly imaged by GPI. During this internship, I basically worked with direct image, learning how to analyze and processing these pictures. So right here, my main goal was to understand the limit of the instrument in direct imaging mode to image asteroids or other faint objects using dim stars. To do this, basically I had to calculate stellar ratio, full width half max, which is the resolution and the contrast curve. In your left-hand side, you can see a graph of resolution versus stellar ratio. As you can see, the best we got, the better resolution we got, the better stellar ratio we obtained. The best results that we got was using the K1 filter. And in your right-hand side, we have a contrast curve analysis. Anything below the lines, you cannot detect. Anything above the lines, you can detect an object. But as you can see, the closest you are from the star, the most difficult it gets to detect something because the contrast is just too little. The best results that we got, well, that I got, it is a best resolution of 52 milliarc seconds with 52% stellar ratio in the H-band. We also obtained higher stellar ratio, which is almost 70%. It's 69, to be more exact. Oops, I'm sorry. And a resolution of 58.7 milliarc seconds of the K1 band. We're currently analyzing the Pallas asteroid, and those results will be presented on the DPS and the AGU Fall Conference. Thank you.
Hello, my name is Lindsay Lesh. My mentor is Dr. Jill Tarter, and and my project this summer is to update the SETI observations database and to calculate the total search volume to date. So this is the official online database on the upper left hand there. It includes the observations made in radio, optical, and infrared. In order to better manipulate the data in the current archive, I wrote an algorithm to export it into Excel, basically all of the data into Excel. I searched many online journals to find any new observations and also any older observations that hadn't been previously included. However, most of the articles in these websites were not attached to their abstracts and had to be tracked down through any online resources or even in our file room here at the SETI Institute. After I'd gotten all of these, all of the information into the new entries, I could then calculate the total search volume that SETI's made to date. So first of all, the total 9-dimensional searchable volume is somewhat arbitrary, but it allows us to make a low estimate. So for each search, the dimensions are all calculated, then multiplied together, and then summed up over the total. So the volume of space being observed is divided by the comprehensive search volume, and the comprehensive search volume can be defined as the volume of a sphere with a 1,000 light-year radius plus the volume of the galactic plane, which can be pictured as a thick crust pizza slice with its point centered at Earth and its crust spanning the galactic center of the Milky Way. Next, the time observed, or the amount of hours spent observing the project. The polarizations observed can be either 1 or 2, depending on whether it's linear, circular, or both. The modulation is the number of types of signals observed. Frequency is divided by the sensitivity, or the amount of power that can be detected based on the type of instrument used. And the bandwidth for radio is calculated, or if it's an optical search, 1 is used. So currently the best estimate that we have is about 10 to the negative 22 of the total 9-dimensional volume. Unfortunately, while researching the current archive, I discovered that many of the entries were in the form that were unusable for calculating. However, I plan to continue working on this project until it's completed. My hopes for the future are to create a database that is very user-friendly for any form of search made on it, to have every article published about a particular search readily available and linked to its entry, to standardize all of the units for all the data contained within, regardless of how it was originally reported, and to allow the database itself to calculate the total search volume with just the click of a button. So I'd like to thank Dr. Jill Tarter and the SETI Institute for giving me the opportunity to participate in this historic project. Thank you.
Hi, I'm Katy Rodriguez. I am a student at Cal State Long Beach. My mentor is Dr. Jerry Harp, and my project is the analysis of SETI's radio signal observation and classification tests. So I worked with the Sonata project, which is the search for extraterrestrial intelligence on the Allen Telescope Array. I used about 5 years worth of archived data to do my project, and my goals were to model the signal drop-off rate across the observation tests, analyze the signal reclassification tests, investigate noise background thresholds, and probe astronomical transient observations for possible retargeting. 2 of my resulting graphs are shown. The graph on the top right is the summary of all of the Sonata data, and it shows that, as predicted, the largest signal drop-offs occur between an on-target observation and an off-target observation. I've been using a 3-parameter log linear fit to model the data, and the graph on the bottom left is just one of the 4 frequency bands that I broke the summed data up into to look at the background thresholds. This is the S-band, which goes from 2 to 4 gigahertz. This, along with its 3 other components and data sets, will be used to potentially set a specific threshold for background noise, as opposed to having one background noise for the entire frequency range. And regarding the transient observations, this kind of became a bigger project than we expected. So a transient is an astronomical event that lasts only a certain period of time. Usually it's a short period, and the event doesn't necessarily reoccur, though it can. And there's potential for these to be sophisticated, engineered extraterrestrial signals, so it's really exciting. And our hope was that there was only a few places in the sky where these transients were occurred. But as you can see, that's not quite what happened. The graph on the bottom right shows the current confirmed exoplanets in an RADET graph from exoplanets.org. The graph on the top right is just one server's worth of transient observational data from Sonata project, and you can see how closely related the 2 graphs are. And the graph on the bottom left are the transient observations from just 3 exoplanet target catalogs. So this, what we hoped was just a few spots in the sky, became a very big part of the sky. So a future project will be to devise ways to isolate interesting transients for re-observation. Thank you.
Good afternoon. My name is Bethany Kelley, and I am a physics and biology double major at the University of Maryland, Baltimore County. My mentor is Peter Juniskins, and I worked with him this summer on reducing the data for the CAMS project, which you can see me doing in this picture. The CAMS project is a network of stations, 3 stations, one at Lick Observatory, one at Fremont Peak, and one in Sunnyvale. At each station, there is a box of 20 cameras. These cameras point at the sky, and they take video of the night sky every night. The goal of this project is to confirm the proposed meteor showers on the International Astronomical Union's working list. The data that is taken by these video cameras is then compiled and given to someone like me to go through and pick out all of the most likely meteors. These cameras pick up pretty much everything that moves in the night sky, so that includes planes and anything else you can imagine. I looked at the data from February and from March, and in February, we observed a shower that we did not expect. In 2011, the Eta Draconids were first observed by the CAMS network, and as you can see, there is a little blob of dots in the upper left-hand corner of the left-hand graph. That's what we're looking for when we go through this data. We're looking for little blobs of radiance. This graph is a right ascension versus declination graph, and each of these radiance is similar to one that was observed in 2011. We weren't expecting this to come back so soon. In 2011, the orbit that was calculated was not expected to be in our path this soon. It should not have come back for another several years. So we're still trying to figure out why it might be, and that's our next step. Thank you.
Hi, my name is Sarah Croker, and my mentor this summer was Adrienne Brown. And the project is titled Water Ice Grain Growth in a 3D Simulated Chamber. And the main question that fueled my project was what happens during winter Martian polar nights? We know a lot about what happens during Mars during the summer and spring through instruments like XRISM, Mars Express, Odyssey, TESS, the Phoenix lander. But we don't know a lot about what happens during winter and when the CO2 deposits cover the ice caps on the north and the south poles. So my mentor has a proposal for an atmospheric surface polarization experiment at nighttime, or ASPEN, and the 2 features that were really relevant to what I did this summer were the multi-wavelength LiDAR, which would be able to distinguish between CO2 ice and water ice at the same time, and then the polarization characteristics of the backscatter determine grain size and shape of dust aerosols as well as on the snowpack. And so my goals this summer were to create a sample chamber for the H2O ice to grow in on top of the thermoelectric cooler, as you can see in the picture on the bottom right-hand corner, and to record images of these ice samples growing, measure the amount of growth that happened, and observe just kind of what the ice crystals did. So a lot of what I did was this process of design, print, and repeat. I used Rhino software to design a chamber, and then I would print it either using the commercial UP 3D printer at the NASA Ames Space Shop, or the Cube Throw printer, which they're beta testing. And actually, they used one of my designs to fix their printer because it kept messing up on mine. It's kind of interesting. And then I just repeat this over and over again until I had something that looks like this. And it has this cap that we can close the chamber and while we're just letting the ice samples grow. And then you can take this off and put a camera on top of it to take images. And then this hole at the front is so we can put the laser and the polarimeter through to look at the samples and take data from that. And it fits exactly on top of the TEC and is kind of perfect for what I did this summer. And so on the left and right sides are the progress of ice grains growing. On the left, we sprinkled some water droplets on and let them freeze up. And on the right is a penny, and we actually just let the water vapor in the lab condense on top of the penny and then grow. And they actually grew over kind of the shape of Lincoln's head and face. And the 2 pictures at the bottom represent a kind of less successful formation of ice crystals because it's very smooth and the ice grains are really fine. It's really hard to put those into ImageJ, which is the program I used to measure how much they were growing, but I was able to do it, and as you can see on the graph, there's some peaks and then there's some valleys, and that happens when the ice will freeze up, but then it will melt off again and freeze up and melt off again, and that's because the lab door was shut and it got really hot and stuffy in the room. So as long as we keep the ambient temperature and the lab down and provide some surface for the water vapors to condense on and make some interesting shapes, we can get some really cool ice crystals, and in the future, we would want to analyze this using a spectrometer or polarimeter, and eventually we would get to use this in kind of with carbon dioxide ice and simulate this in Mars conditions kind of atmosphere. Thank you.
Hello, my name is Divya Prasad, and my project this summer was methods of estimating initial crater depths on icy satellites using stereotopography. So icy satellites, or icy moons, are moons that are dominated by ice composition. The Cassini mission, which reached the Saturn system in 2004, has helped us study these icy moons of Jupiter and Saturn. Craters are an interesting feature on these icy moons because studying the relaxation or general flattening with time of these craters can help us understand the viscosity of this ice with depth, and thus temperature or the geothermal gradient of the bodies. So to understand the degree of relaxation of these features, you need to know the initial depths of these craters. The literature describes two methods of estimating initial crater depths for the icy moons Rhea and Dione of Saturn. The first presented by my mentor, Cynthia Phillips, and the second by White and Schenk, both in 2013. So I tested these methods. First, I took the digital elevation models constructed from Cassini data for the icy moon Iapetus, and I extracted topographic profiles. So you can see in the upper left is a DEM, and in the bottom is one of the topographic profiles I extracted from that image. And I derived the depths and diameters from these profiles. So for the first method, I assumed that Herschel crater on the icy moon Mimas was unrelaxed, and I scaled craters from Iapetus to Herschel and calculated initial depths and relaxation percentages of Iapetus relative to Herschel, and compared these relaxation percentages to those of Rhea and Dione. For the second method, I assumed that Iapetus was largely unrelaxed and calculated initial depths and relaxation percentages of both Rhea and Dione relative to Iapetus. So these are my results. On the left is the first method, where diameter is plotted, it's diameter versus relaxation percentages for Rhea, Dione, and Iapetus relative to Herschel. Iapetus is shown in red. As you can see, Iapetus is far more relaxed than both Rhea and Dione. The second method is on the right, where Rhea and Dione's relaxation percentages are plotted, scaled from Iapetus. And both have significantly negative relaxation percentages, which means Iapetus is far more relaxed than both Rhea and Dione. So both methods seem to show that Iapetus is significantly relaxed compared to Rhea and Dione, and thus Cynthia's model holds against White and Schenk's. So future work includes studying Iapetus's thermal history, which very clearly is different than Rhea and Dione's. Thank you.
Hello, my name is Tiana Schneiderman, and my job this summer was to develop an adaptive multi-sensor data fusion model for in situ Mars exploration. Basically, I was tasked with taking Raman spectra and microimages and developing a method to combine the data for more complete mineralogical characterizations. In simplest terms, Raman spectroscopy consists of shining a laser on a sample and observing the light produced. The laser excites electrons based on vibrational states of molecules within the sample, creating a unique molecular fingerprint. Microimaging is useful because it reveals information about the morphology and texture of a rock. By fusing this data, microimaging can inform and enhance Raman characterizations. This method is in high demand for planetary science, as evidenced by the presence of a Raman spectrometer and microimager on board both the Mars 2020 payload and ESA's 2018 ExoMars mission. In order to utilize my data, both images and spectra needed to be pre-processed. To deal with spectra, I first had to remove background emission. Each spectrum has a unique background that my algorithm detects and subtracts. I also incorporated smoothing and normalization into my code. To pre-process images, the original microimage was brightened and the contrast increased to enable feature detection. In this brightened image was then clustered based on texture to reduce the number of features. In this first image, there were a total of 265 possible pixel values. In the second, the number was reduced to 4. Next, I extracted features. Spectra were treated through principal component analysis, a statistical method that uses orthogonal transformation to convert a set of variables into principal components. A histogram was produced for each image describing pixel clustering. Our goal is to associate these extracted features with mineralogical information. The last step is to fuse the data acquired to achieve a conclusive identification. The images had between 4 and 5 classes, as seen in this graph. Each line represents the counts per class of a single image, and each histogram is different, describing the variations in pixel distribution between images. I'm currently working to understand how this distribution informs sample composition. Spectral analysis yielded a 3-component model. The samples cluster along mineral composition, and as can be seen here, the sphalerite class is highly dispersed, indicating the need for additional samples and data fusion to identify sphalerite variations. I will be continuing this project after the end of the summer. My next to-do item is pre-processing laser-induced breakdown spectroscopy data. After extracting features from all 3 datasets and associating the features with given minerals, I will pass unknown samples through my program and assign scores affiliating them with a class. Once individual determinations are made from each set, results will be fused to make a joint identification. This work will be presented at the AGU Fall Meeting in December. Thank you.
Hi, I'm Zarek Smith. I'm a physics student at San Jose State University. And this summer, I've been working with Dr. Pascal Lee of the SETI Institute on PADME, which stands for Phobos and Deimos and Mars Environment. It's designed to explore the 2 moons of Mars, which are Phobos and Deimos, pictured here in their relative sizes. Deimos, on your left, is the smaller one with largest axis of approximately 15 kilometers and relatively smooth features, not a lot of cratering. Phobos, on the other hand, is about 27 kilometers on its longest axis, has a lot of cratering, including the rather large crater on the right of the image named Stickney, and very odd linear groove patterns that you can see there radiating from nearby to Stickney. I was given a fairly easy sounding task. Dr. Lee asked me to identify features of interest, such as boulders on the surface, and everything was going quite well until I realized that there were literally thousands of them. So I wrote custom software to identify such things. On the left, we have an unprocessed image of a boulder cluster. And in the center, you can see after processing, the algorithm identified the boulders, highlighted them with blue, and made it a little easier for us to see where things are. On the right is an implementation of photoclinometry and showing some of the features there. This is one of my favorite images, actually. It's a wider view of the previous boulder cluster, which is up here on the right of the screen. But there's also several red dots that highlight boulders, some of which were previously unaccounted for by our team, thusly aiding in our targeting of these features of interest. Also, the craters in this image, you can see the smaller craters that are newer are highlighted in blue, while some of the older, more relaxed craters were rejected by the algorithm, which is exactly what we wanted. In the future, I'm going to be implementing a version of control point networks and 3D mapping of these features to create a 3D shape model to aid in our targeting of future missions to these moons. Thank you.
Hello everyone, my name is Ruth Valenzuela. I'm an electrical engineering major at Cal Poly Pomona. I'll be talking about my project toward building a rock classifier, which I have been working on this summer with my mentor, Dr. Jenny Gulick. The purpose and motivation of this project of building a rock classifier is to assist in field analysis of geological samples in terrestrial rover missions and hard to reach or dangerous locations such as this active volcanic site where this guy seems to be having the time of his life. We also seek to provide insight on the history and formation of a site. One way that we can gather this knowledge is by using Raman spectroscopy, which gives unique chemical signatures of minerals. I will now begin talking about developing the classifier. Developing occurs in two stages, training and testing, which follow the same process as the flowchart illustrated in this slide. In training, we input labeled known Raman spectra of a database of rock samples and pre-process that spectral data to remove noise due to background fluorescence, which occurs during spectroscopy. The filtered data is then passed through principal components analysis to reduce dimensionality. This processed data is then input into a learning algorithm called the multi-layer perception, which is based on artificial neural networks. This artificial neural network essentially learns by example. So, in other words, it generalizes the relationships of the spectral data that is passed through the algorithm. The algorithm outputs probabilities that will associate Raman spectral data with particular minerals. We can also input unseen and labeled Raman spectra to test the classifier for accuracy. In conclusion, using Raman spectroscopy to classify rocks or any other geological samples can give us a lot of insight on composition. However, this can be taken a step further by including previous imaging work, which analyzes rocks based on color and texture. This will allow us to obtain a more complete understanding of rock samples. As seen in the slide, imaging plus spectral classification gives us a better classifier. Thank you.
Good afternoon, everyone. My name is Renee Milan. I'm an undergrad at Cal State University of Los Angeles. I'm studying civil engineering and physics. My mentor this summer is Friedman Front, and we are researching the manipulation of the flexure strength of rocks due to electrostatic fields. So to give you an introduction to the underlying process that we're researching, there are many materials, such as magnesium oxide, that contain what are known as proxy defects. And this is a proxy link between two oxygen anions with a missing cation. What happens is when we apply a stress, these proxy links are broken, and an electron from a neighboring anion is shared with that bond. And this creates a charge carrier known as a positive hole. These positive holes can propagate outwards through a quantum mechanical process. And what happens is, instead of an individual oxygen anion sharing a single electron, a region of multiple anions feel the need to share a portion of the electron density. So what happens is there's a general reduction in the overall electron density to where each of the anions has about a negative 1.99 charge. So due to this reduction, the strength between the cation and anion bonds is weakened. And this leads to a change in the mechanical properties of rocks. As you see in the bottom panel, we stress a rock slab in the center, and this stress breaks up the proxy links. The positive holes propagate outwards to the edges, and what we do is we apply an electrostatic field, a positive charge on the edges and a negative charge in the center. This chases the holes back to the center under the stress, and due to a concentrated region of weaker bonds, we see a reduction in strength of the rocks of up to 15%. So we have two different experiments going on this summer where we're trying to test this process. One is here at SETI and another at NASA Ames. You can see on the left, the SETI experiment, we are using a cross-shaped gabbro slab of rock. We use ultrasound transducers at two opposing ends to break the proxy links. They're chased to the free ends. We use an applied electrostatic field to chase them back to the center. And we should see, using deflection detectors, a sagging of the free ends. Over at NASA, we're trying to determine whether or not these proxy defects exist in the acetate of bones. So what we're doing is we're using bovine femur from a cow, and we're cutting down samples to about the size of 20 millimeters with varying widths. And using a 3-point bending system, we will apply stress and see if the response of the strength will be the same between no applied charge and an applied charge. So that's research I've been doing. Thank you for listening.
Well, those were excellent talks. Let's thank our speakers one more time for their great research projects. Now I'd like to open up the floor to any of you who may have questions, either to me about the REU program or to any of the students about their individual projects.
I'm curious about the follow-up. Nearly all your speakers said they plan to continue this work, yet they're undergraduate students with a class load of work and they're coming for the summer. How exactly is this continuation going to be handled?
Very carefully. Of course, their schoolwork comes first. But we have had students in the past who continue throughout the semester, even if they are not located here locally. They continue either as a senior thesis project or just several hours a week finishing up the work that they started here. We also have two students that are staying a few extra weeks and actually a few extra months after the end of this program to continue to work with their mentors.
And when you were younger, remember, you didn't sleep, you just worked.
Are there any other questions?
Yeah, I'd be interested in how many of the students are already planning with their mentors for a poster or a talk at a scientific conference.
Looks like 90%, just for the people who can't see those hands.
Yeah, so most of our students are planning either to go to AGU or to the AAS meeting, which is in January of 2015. So, any other questions?
Can mentors ask them?
Well, we saw all the students. Why don't the mentors that are here raise their hand, because they all contributed a great deal, or stand up to the students? Great. I see some hands up. Super.
For the online audience, there was 14 people standing up.
That's right. So we had 14 students and 14 mentors, so it's one-to-one correspondence. Okay, are there any other questions from the audience? No? If not, I'd like to again thank the mentors, the support staff, the NSF, and the various other programs that have helped support the students this summer. So let's give another round of applause, and then we'll call it a day. Thank you.
Oh, and Jean, just for anybody who's thinking about applying for next year, maybe you could let them know that the REU program will be going ahead. And
yeah, so the REU program runs every summer, or has run every summer for the past 8 or 9 years now. Applications, I believe, are usually announced around November and are due early February, if I remember correctly. And we announce decisions by mid to end February, and that's fairly standard across the country for various other REU programs. Okay. Yes?
What are these things on the front table? That's all.
Yeah, Sarah, if you want to come up.
I completely forgot to point to those, but those are all my failed sample chambers that I designed with a 3D printer. The big brown guy was the first thing I did. I was just trying to figure out how to make a hole inside. Actually took me a really long time because I'd never used this kind of software before. So that was the first one, and then the black one towards the end is probably one of the last ones I did, and then I didn't bring the actual chamber we ended up using up here, but yeah, those are all just some various things that I printed, and I was supposed to point to them during my presentation, say, hey, look at all these things I did, but so here it is now.
Okay, one last call for questions. No, if not, let's wrap it up then for today. Thank you.